Hello, class.
Hello, sir.
Yeah. How are we?
We are fine.
Now, patients, are you okay?
Yes, sir.
Yeah. We are back for another wonderful time in the subject. We looked at the first topic. We are on senior 2 work, and we have already looked at topic 1, and we saw that was acids, bases, and the indicators. Yeah. Then our topic 2 will be salts. Salts. Now, listen. Before I drop in salts, let me bring this to your attention first. Under topic 1, we last ended with indicators. Then we gave several indicators, including the universal indicator, and I wanted you to research on the behavior of organic indicators from plants. Organic indicators from plants. So now, as mentioned earlier, I told you that colored petals and flowers of plants, whenever you find a colored flower, that's an indicator. So it can be yellow, it can be red, like the hibiscus flower, it can be blue, see, red, hibiscus flower, blue. Some fruits are also indicators, like the beetroot, see, the onions. The onions. Now, the color of like an onion juice is purple. And if you drop in an acid, it will not change to the colors of other indicators, no. Because when you saw methyl orange, if you dropped in an acid, it turned red, but phenolphthalein remained colorless. That means if you drop in an acid in the onion juice, you expect a different color, not even on the universal indicator chart as it should follow. You can drop in onion juice, you can drop an acid in onion, like lemon, you drop it into an onion, it turns to another thing. But what you should keep in mind that you can generate your indicator and find out the onion in an acid turns to which color, and the onion in alkaline medium like soap turns to which color. Then it can aid you in your domestic simple experiments like making soap at home. Yeah, because you need to test the alkalinity. You can find out an onion in an acid turns what. Then when you are using it to find out alkalinity of your soap, it could work. Now, before I usher in salts, these indicators here are extracted from flowers. Beetroot is extracted from beetroot, and the onion from onions. In 2 minutes, I will request patients to give us guidelines how you do prepare an indicator from hibiscus flowers, and Chirabo takes us how you do prepare an indicator from onions. Then we can now shift to our salts. Yes, patients, how would you prepare an indicator from hibiscus?
First of all, this is a hibiscus flower. It has pink petals, and any flower with any color of petals like blue, pink, yellow, they are all indicators. So, how to prepare an indicator from a hibiscus flower? You get the petals and boil them in a little amount of water using a beaker. After boiling, you can take off the heat source, and then the water will have turned to purplish pink, I think purple. Then that liquid that comes from, if you filter the hibiscus flowers and the water, then you use that water you use that water as an indicator when you're looking for alkalinity or substances.
Okay, thank you. Maybe you only left out one thing, that you would pound those flowers, then add water after pounding. Okay.
Okay, when it comes to the onion, you can simply peel it, cut it into small pieces, and then you boil it. The level of water that you can put is just like a quarter of the beaker. We boil it. After boiling it, we shall filter to get the fine solution. The fine solution will be colorless, and then we shall use that solution as an indicator by adding in this methyl orange or using the litmus papers.
Okay, thank you, Chirabo. Though you have mixed the chemistry, you have developed new chemistry. See, it means you were again preparing a universal organic indicator, because you are telling us you get the onion indicator and again adding methyl orange indicator. That means you are preparing a universal one now. You see, now an onion indicator, as you cut those red onions especially, they are better off. Yeah, very, very red. You cut them into tiny pieces, boil in a measurable amount of water, cool, filter. Chirabo said the color would be colorless, but definitely you've ever done it and you saw the color was purple. Yeah, purple. So I think you can try that at home. Then you can use it to test whether the pineapple is acidic or it's not, by first getting prior knowledge using standard acids and alkalis. Okay, you can do more research on various flowers, how they interact. Google will show you very well. Just type in beetroot indicator, it will show you. You can go on YouTube, say the same, hibiscus indicator. You will see YouTube videos on the preparation and the use. Thank you. Now, in the interest of time, today we are opening broadly another topic called the salts. This is topic 2 of senior 2 work. Topic 2. Pay attention, because all things you have them at home. See? Yeah, but you might not be aware that you are having an acid or a salt or an alkali or a base, but you might be having substances. Now, we want to know this salt, because some of you would think the word salt means table salt at home. No? Though table salt at home is salt. See? Now, under here, we shall visit meaning of a salt. These are the subtopics. Meaning, what does that salt mean? See, does it mean table salt at home? Meaning of a salt. See, now we also visit formation of a salt. How is a salt formed? See, and I believe some of you have already prior knowledge on how a salt is made, is formed. So we shall also visit, see, naming salts. Naming salts and their examples. Then types of salts. See? Then we shall visit soluble and insoluble salts. Soluble and insoluble salts. See? Then we shall also visit and their preparation methods, and how do you prepare them, and how do you prepare them. See? Then we shall also visit how do you prepare them, properties of salts, and lastly the uses of salts. Indeed, are those things relevant, or we just keep speaking and speaking and speaking? See? Now, pay maximum attention here. Let us start meaning of a salt. What does the word salt mean? What does it mean? Yeah? Now look here. In reminder of previous topic, we said there is what we call neutralization reaction. Then I would pose a question. What is a neutralization reaction? See? Yes, Shirabo, you seem to be having the answer.
A neutralization process is a process that occurs when we add an acid to an alkali.
Good. Let us see patience whether she will add more.
A neutralization reaction is a process of adding an acid to an alkaline to produce salt and water.
Only. So, Chirabo, you agree? You don't? Chirabo, why don't? Can you give us one reason why you don't? You agree that a salt is a neutralization is a reaction between an acid and a base to form a salt and water only. Now we are saying that now because we are still on the meaning of a salt. Now we are saying that when an acid is added to a what? to a base, then you must form a salt plus water. Listen, we said an acid here has a chemical part called hydrogen, and having hydrogen in it is not the only part, because you have the active part and the other parts. It has hydrogen ion and a non-metal part on it, non-metal ion. It has a hydrogen ion and a non-metal ion. See, then a base had an active part called hydroxide. Clear? Hydroxide ion or oxide. Then, now listen, an acid has hydrogen and a non-metal, while a base has hydroxide and a metal ion. Hydroxide ion, it has a metal. That's why you say an example of a base was sodium hydroxide. Did you say so?
Yeah.
Sodium hydroxide. That meant that you mentioned a metal and hydroxide. Now ahead there we shall also see that another term for hydroxide we normally, because you'll meet these things in your research, you'll hear the word hydroxyl. A hydroxide or hydroxyl is the same language. Hydroxide and hydroxyl ion. See, it's the same thing. Now, listen. During the reaction, the base has to mix to form new things by exchanging elements or ions. See, the metal ion in the base, patients are either, will replace the what? That means metal comes here and joins up with the non-metal. Then this hydrogen ion joins with hydroxyl ion. Now these ones here, you must be really watching closely here, because the technique of the salt here is a bit really demanding. See? Now, because we are trying to see what, see, the hydrogen ion takes up hydroxide ion to form, then the metal ion and the non-metal part forms. Listen, we have an acid. Let me take you to an example. There is an acid called hydrochloric what? Acid. Listen, if there is hydrochloric acid and we said each acid has elements in it, this one has hydrogen and chlorine. Now, hydrochloric acid salts will be called chlorides. So what are you talking about? Now you listen. Now we are saying that this one, that means if we are like reacting hydrochloric acid with sodium hydroxide, sodium hydroxide, this hydroxide will mix with what? Then this sodium will mix with now the salts of hydrochloric acid are called chlorides. Salts of sulfuric acid are called sulfates. Salts of nitric acid are called nitrates, and salts of carbonic acid are called carbonates. Now, that means a salt, what is the component of a salt? The salt has what? It has a metal ion and a non-metal section. That means a salt formed from hydrochloric acid and sodium hydroxide will be called what? Sodium hydrochloric acid plus sodium hydroxide. What do you form? Because we are saying hydrochloric acid, salts are named from the acid they come from. These are called chlorides. Sulfuric acid gives us sulfates. Now which salt will be formed there? See, it puts your head at breakneck. I want a think tank. Are you guessing? Say it again.
Sodium chloride.
That's very, very accurate. See, she has even wondered how the answer could be correct. Sodium chloride plus water. Now, listen, the concept of writing equation, now here we are writing them in words. See? In your research, I think you made equations written in symbols. You made some symbols, H like H and Cl. That concept we are going to carry it forward ahead of time there to senior 3. But for the interest of time here, we are saying learn to form equations there from words. See? Keeping in the mind that a salt from hydrochloric acid must be called a chloride. See? Yeah. Now, even though, you see, let me tease you a bit. Nitric acid, see, plus magnesium oxide, which salt will you form? Yes, Jirabo.
Magnesium nitrate.
Plus? Period. Water will come from the oxide is a transformation of oxygen to oxide when you have formed a compound. Now, sir, what do you mean? That when an element has a name in its isolated form, that oxygen, when we are talking about oxygen, we call it oxygen in elemental form when it is not in combination with anything. That is but when we have it read with another element in compound form, it changes to be called an oxide. Now let me ask, why is the chlorine in hydrochloric acid, when we are with sodium, we read sodium chloride. In compound form we are not reading it as sodium chlorine. That's why the salt is a chlor. Exactly. Yeah. Now, me, I want to ask you a question from those discussions. What is a salt? What is a salt? Because now I want to say the meaning, or the actual meaning of a salt is what now? Now you seem to be burning with an answer. Go ahead.
So I'm going to
Try.
Okay, a salt is a combination of both a non-metal ion from an acid and a metal ion from a base.
See, that's very, very good. Do you have a different view? Sense? No, you don't. It is so interesting here that she has almost been exact, but to be, now let us try to move with our answer. That a salt is a substance formed when a metal ion of a base not so, replaces the hydrogen ion in the acid. Not so? Now there she gave us the meaning that a salt is containing the metal part from the base and the non-metal section from the Precious, are you already seeing how things don't mean that the salt we are talking about, that it does not always mean the table salt you enjoy at home? Of course, it's an example, because at home the salt in fact that you eat there is called sodium chloride. See? That's why now when you go back home, you tell the parent, please, sodium chloride is over. Don't say, Father, salt is over. When they ask you what is sodium chloride, say, look what, tell them. Not so? Now, see. Now, meaning of a salt, that means under meaning, we shall put definition and its chemical nature. Definition is that a salt is a substance formed when all or part, you've left out something there, all or part. Now we are modifying it better. Now you would wonder, now where does the word all come in? Here, look here. Let us first finish that definition. Formed when all or part of the ionizable hydrogen atoms of an acid are replaced by a metal ion or ammonium ion. There you are. Are replaced by a metal ion or ammonium ion. There you are. So what do you mean? See, I want to explain this word all or part. Now remember, listen, and I want also, you see, before I explain that, there is this. Let me put this to hang in your brain first. There are some salts called, like we have ammonium nitrate, which is a fertilizer also. Now listen, ammonium is not a metal, of course. Not so? But we have sodium chloride. Sodium is a metal. Now, some non-metallic group of elements are called ammonium, also form salts. We saw ammonia under bases the other side. Ammonia, when it attacks, when ammonia meets an acid, it forms ammonium salts. That's why we are saying that you can read the salt as ammonium chloride, but of course ammonium is not in the periodic table, but it's ammonia is a base which reacted with an acid to form a salt called ammonium salt. See, that's why we are saying that either the hydrogen will be replaced by ammonium ion or a metal. That's why when you read ammonium sulfate, ammonium nitrate, don't wonder that now where does ammonium come from? It's a group of non-metal atoms which can also form salts. See. Now let us move. Now I want to explain deeper here on these two statements that a salt is formed when these hydrogens, all of them are replaced or part of them. Let me pause here. Now, let me ask you something. There is where we talked about basicity of an acid. Did you remember? Yeah. We said, what did basicity mean? So somewhere we said the basicity meant number of hydrogen ions that one molecule can put in solution. Now listen, some acids have 2 hydrogen ions in their formula. You need to listen there. Some have, we say an acid can have 1 hydrogen ion, another acid can have 2, another acid can have 3. Now when the metal from a base is replacing the hydrogen, if you have 2 hydrogens, it can replace 1, leaving 1 in your structure, because if the acid has 2, therefore a metal from here can use up 1 space, leaving another hydrogen inside. That's why we are saying some reactions can involve replacing all. That's why we are saying that when part all is replaced, that will mean that it depends on the basis of the acid, whether the acid has 2, 3 or 1. That exact. See, now listen. It draws us now to the meaning of a salt, which we said that a salt, she told us that a salt has what? A salt contains a metal ion from the base and a non-metal ion from the acid. Period. Now, meaning is over. Formation of salts, we've already seen that. Salts are formed when
we combine the acid and base
by a reaction called
neutralization.
So, that's very deep. But we added a statement that the acid can, that the metal ion from the base can replace all the hydrogen ions, or can replace part of the hydrogen ions in the acid. See?
Acid plus base. Why
Yes.
is there equals to salt plus water?
Oh. See, that why don't chemical equation is acid plus base equals salt plus water. And then I'm also going to ask you that is this saying correct? To this one is equal to that. Is this correct?
No?
Somebody saying no.
Yes.
Oh, it is yes. Okay. Now, equal signs mean that things are the same. But an arrow means conversion from one type of thing to another type of, because a chemical reaction is a transformation from what we call, this side is always called reactants. Things that are reacting are being changed to other things called. But when you say equals, you mean that these things are exactly the same as, yet an acid will taste bitter, an acid will taste sour, a base will taste bitter. A salt will taste. There you are. The reaction is called neutral. And we said to be neutral is to taste tasteless. See? Yeah. Okay, now formation of a salt, we have seen how a salt is formed, not so? Now, e.g., you would put there some examples. See? E.g., you write acid plus base is equal to salt and water. Then we put here something and we directly run it to. Do you love the chemistry? See, it is hydrochloric acid plus what? A base like sodium hydroxide will give you who?
Sodium chloride plus water.
Sodium chloride. That's very, very true and exact. See? Yeah. Now let us look at naming salts, and we give several examples now here. How are salts named from our discussion?
Chemical substances that are formed when four parts of the hydrogen, one ionizable hydrogen atom of an acid are replaced by a metal ion.
That's correct, but you have refused to give me my answer.
You said what's the name also?
No. You can try.
Okay.
What was the question?
How do we name salts?
Oh.
Okay, we can name salts basing on the names of the non-metals and the metal ions. Just like the sodium chloride, we based on chlorine, which is a non-metal ion.
Okay. That's very, very correct. Now there. How do you name patients? The same way?
Yes.
Okay. Now, we can, that's very, very correct, but now it is very, 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 very deep inside there. How do you know the non-met? Sometimes it's very, very hard inside, like sulfuric acid. Salts are called sulfates, not so? We can say salts are named depending on the type of acid, not so? Depending on the type of acid they are formed from. See? That's very, very great work. Yeah. E.g., acid, name of salt. Now, we said, at first we said hydrochloric acid gives us which salt? Yeah. Hydrochloric acid gives us salts called chlorides. E.g., you can list some theory. Have you listed? What have you listed there? Sodium chloride and what else? Calcium. Sulfuric acid gives us what we call sulfates, not so? e.g. you name them. Then we have nitric acid gives us nitrates. Nitric acid gives us nitrates. There are so many acids. Phosphoric acid gives us phosphates. Yeah. And you to give them phosphoric acid, phosphates. There you are. Now you read many acids. Nitrous acid gives us nitrous acid. What do you get in nitrous acid? The other side would be named as nitrites. See? Of course, many salts, the more you name them, you see those salts are found in your drugs. See, go and look at the components of your drugs. See, you'll find the label indicating citric acid, aluminium sulfate. You'll find it written on the drug section. That means salts are so important. See?
Teacher, salt names are really good for mineral acids. Only mineral acids.
No. Of course, we have some organic acids like lactic acid giving us lactates. See, citric acid, citrate. See, yeah. But the method of getting a salt from an organic acid is quite demanding. It's not the one of the. It's rare. Though we can do some in the laboratory, but few. Most of them are made at industrial scale. See. And those most organic things are what makes your tablets, if you knew that all drugs are got majorly from herbs. Yeah, it's just that we try to, we normally just realize later that the drug is from the trees that are around us. See? You heard of Dr. Ogwanga who discovered the Covidex. So, Covidex. Yeah. Now if you can study the chemical parts, now we shall see as we move on with this chemistry that you can extract those chemical compounds in those materials. You see, personally, I've tried to study how these plants, the chemical compounds in those plants, and it's just Google work. Check which compounds are found in, say neem tree. They will list for you. Then Google also what is the use of this compound in the neem tree. They will tell you. Then you learn that this tree can heal malaria. See? Yeah. Mululuza. Google up. You'll find. See? You'll discover the chemical compounds inside and learn their uses concurrently. So don't be there, you die. I don't have money to go to the hospital, yet you have trees. Check, not so? You're a chemist. That's true. Now, that throws us into what we are calling examples. You have given examples under each? Yeah. That's so great. Put for me some equations down there to form what you have put. The acid that you used and the product, acid-base product. Even when you use an oxide, it's okay. Magnesium oxide plus hydrochloric acid, what do you get?
In what?
Yeah. You use plus. Yeah. Have you seen that? Okay, you'll put more when you are having some revision time. Read for me one of yours, patients, starting with you.
Sulfuric acid plus potassium hydroxide gives us potassium sulfate.
Only?
Then,
Stationary didn't include in mine.
Okay, but you left out something. You get potassium hydroxide only?
plus what?
Yeah. Collaborate.
Hydrochloric acid plus zinc oxide gives us zinc chloride plus water.
That's right. Now that's enough. Let us turn to types of salts here. Yeah. Types of salts. Yeah. Now, let me mention for you these two salts here. There is this salt here, sodium carbonate. What acid do you think it can be made from? It can be made from which mixture? Which two compounds can you mix?
Sodium hydroxide.
And which acid is that? Carbonic acid. Now, there is also this one called sodium hydrogen carbonate. Now look at the two differences. This is called baking soda. Baking soda. It's also found in baking powder. Baking powder is not baking soda, though both of them have the active ingredient as sodium hydrogen carbonate. This is called the soda ash. The active ingredient in ash, soda ash, which they call it in which local language it's called? Magadi. You know Magadi? That.
It's a place in Kenya.
Yes, but there is a certain gray looking substance called the magadi that they put in gobe when they want it to be made magadi soda ash. See, this one is even applied in water when water can't form leather to soften it. See, this one is used in baking powder. See, now these two, one is read as sodium carbonate, one is sodium hydrogen. One has, it did not give out all its hydrogen, therefore the hydrogen remained inside the acid. Because we said earlier on that a salt is formed when all or part has been replaced. Now this one did not permit all of its hydrogen atoms or ions to be replaced. See? But this one permitted replacement, total replacement. Therefore, you can't read any hydrogen in it. That's very, very correct. Now, this creates to have a special type of salts for total replacement of all the hydrogen is called a what? See, a normal types of salts, normal salt and acid salt, acid salt. That means the normal salt is a salt formed when all the ionizable hydrogen atoms of an acid have been replaced, all have been replaced by a metal ion or ammonium ion. Then consequently you define for me acid salt, you even give an example. Yeah, I think that's it. When part has been replaced is this. When all has been replaced, that. Now, soluble and insoluble salts. See, soluble and insoluble salts. And how do we prepare salts in the laboratory? And now you see some salts are there, you can look at them. You can look at those things around you, these ones. Those are salts. See. You are seeing cupric carbonate. That's some names that were first given to substances. Cupric. Copper salts were called cupric. But earlier on, when there was improvement in this science, there is a body that normally agrees on the naming of these things. See, the body now improved the names from cupric to copper. That's why here you read the copper sulfate here. See, zinc carbonate. Now I think you're seeing them inside. We are yet to look at properties. If you look inside, some are like powdered, some are like what? In crystal form. Some colors are different. See, that's so wonderful. Yeah. Some are in crystal form. Is that very, very correct? Powdered. You can point one to the camera. Which one are you holding there?
Zinc sulfate.
Zinc sulfate. Inside, cupric carbonate, but it's called the copper. The metal is copper. Copper. See, now the names were improved by the international naming body. You see, scientists struggled a lot to make improvements. Some even were thinking of, you see, somebody could think that copper is a compound. But now for us, we are enjoying things which are free, not so. We know that copper is a metal or an element, but for them they struggled with wrong work. A professor is struggling calling copper carbonate as a metal, you see. But now these days life is easy, not so? Mendeleev, those great scientists, Socrates, those Democritus, those who discovered the atom, first thought wrong things. See, but now they are wrong things. They were correct things which they didn't know very well. Now slowly knowledge increased. See, yeah, they could call a metal as a compound. Yeah, but now we call them correctly. Now look here, soluble and insoluble salts. Clear? Now, to understand this concept, you see we have built very much on a salt. Now, if I ask you a question, is sodium carbonate a salt, a base, or an acid? There you are. That is, keep in mind, an acid we have seen, see, therefore don't be deceived. Yeah. Now, to understand what we mean by to be soluble, you are doing a simple test there. Each one you will get a test tube and add about 4 cubic centimeters of water. Now use 5 cubic centimeters of water, and you'll what? You'll add 1 spatula of a salt, I'll tell you. 1 spatula. Then you'll shake vigorously like this. 1 spatula, 5 cubic of water. We should use a measuring cylinder, but since we don't have it currently, you can put some approximate water almost halfway. Which salts are facing you there?
Copper carbonate, zinc sulfate.
Now, for you absorbing 1 spatula of zinc sulfate, that's too much water, is almost full. Bring it halfway. Yeah. 1 spatula. Now, you'll use a zinc carbonate. Also 1 spatula. Because we want to know to soluble and insoluble. Yeah, that's enough. Yeah. Now you shake thoroughly and tell us whether what has happened. You must shake with energy. That's how you can carry out if they say dissolve 1 spatula of this, you do that, you dissolve. See? Yeah, now what has happened? Tell us. Let me have this one here. Who is this? Tell us what has happened.
When I mix zinc sulfate and water, the zinc sulfate dissolves in water.
And it's no longer being seen. See, no longer being seen. Out of patience, what has happened?
It has not dissolved.
It has not dissolved. And what are you seeing?
Particles of zinc carbonate going down.
Going down. Down and up is becoming.
Where?
What does it mean by up becoming clear?
Because these particles are resting at that bottom.
Who is up there? Water. The whole mixture is called a suspension. Yeah, a suspension is a mixture containing suspended and dissolved particles. See? It occurs when you add something to water that cannot dissolve. Yeah. Now, it means some salts are soluble while some are not. Now, see, that means soluble salts form solutions while insoluble salts form suspensions. Does it mean uninsoluble salts can be separated back? A suspension, you can filter it back. See, now listen. Now how do you, because that zinc carbonate powder, if you filter it back, it will be, what will it be dry?
No.
How do it dry?
By heating.
See, by heating. Now listen, that's very, very good. Now in the laboratory, substances are not directly just heat. Listen, you don't just, well, because we say the heat is one of the conditions under which a chemical reaction can take. That means when you heat, you can cause a chemical reaction. The best way is to dry. Now how do we dry? We put the wet substance between pieces of filter paper. Between pieces of filter paper. The two of them. Now, when you filter, we can just demonstrate to save time. I think you know how to filter, you know how to fold the filter paper. Yeah, because we are going to need that. When you have your residue here, you open the filter paper. Then you get another filter paper and you try to squeeze them together. See that? When you squeeze, one filter paper absorbs water, leaving this part dry. Then you can put it there under a what? After removing water, you can put it there in little sunlight until it totally waters, dry the papers, and you transfer back to the tins. That's the chemistry, because now we are going into depth here. See, we are going into depth, you must understand. Now, we said soluble salts form solutions, insoluble salts form suspension. Exactly. Now, principles of solubility. Now there, we are just drawing a table here to just capture who is soluble. Oh, you mark there. Now let me ask you, which salt was soluble? Which type?
Zinc sulfate.
A sulfate. Now look here. All salts of potassium I don't know whether somebody will seem to see this. Sodium and ammonium are soluble. What do we mean? That when you read potassium sulfate, potassium nitrate, ammonium carbonate, anything you read containing that metal called potassium or sodium, however type it is, it will dissolve. Is ammonium chloride soluble? Yeah. Because you have said anything mentioned with them is so. See. Now go ahead. Next part, to save time. Yeah. All sulfates are? Are you sure did that sulfate did not dissolve in water? All sulfates are soluble except, now there are only few among them. All sulfates are soluble except lead 2 sulfate, barium sulfate, and calcium sulfate. Someone say, now what is barium? Barium is a metal in the periodic table, not so. You can check our long periodic table there. You'll find barium, except barium sulfate, lead 2 sulfate, and calcium sulfate. That means when you pour calcium sulfate in water, it will form a suspension. All chlorides are soluble except lead 2 chloride and silver chloride. That's now very deep there. You continue there that lead 2 chloride dissolves in hot water and recrystallizes on cooling. Recrystallizes, open bracket, reappears on cooling. Now, that statement is funny. See, what do we mean by that lead 2 chloride is an insoluble salt, which is very, very it's very, very funny. Let me show it to you here from this, I show something here. Something very, very small here. Now, lead 2 chloride. When you have put lead 2 chloride in water, it is like this, like it was here when you dissolved zinc carbonate, not so? But when you heat this on fire, it will disappear. You'll see colorless. When you cool it in water, when you cool in water by cooling the test tube, it will come back to this. Yeah, you want to try to see it? Yeah, it is okay. You can heat it broke. Sorry, you don't hit in direct what? A scientist does not fear. Heat in a gentle. Lift it a bit up. Yeah. Shake a bit up. Yeah, show up, lift now. Wait and we see. Wait, and you can wait from there. You can wait. No, just pause from there. You can remove away this and use. Put on the rack. No, you were to hit this one. Because they wanted to say to disappear and to reappear means what? Patience, why are you fearing very, very much? Shake. Lift it up. Yeah, lift it up to see. Lift it up, remove from fire. Is it clear inside? Put it up there. Does it still have the solids? No. But when we cool and wait, the solids will form back. You can blow off. Yeah. It dissolves, and when you cool the solids, it appears a suspension again. Which salt behaves like that? Lead to chloride. You understand that? It is the only salt that has a behavior of dissolving in hot mixture and reforming in cold mixture. Now proceed. Are you through with chlorides? Then all carbonates are insoluble. They don't dissolve. Except those of these ones, because we said for their salts all dissolve, except for potassium, sodium, and ammonium. Then all nitrates are soluble, all of them. There is no exception. Now, it throws us to preparation of soluble salts, preparation of soluble and insoluble salts. As we try to summarize up, I think you've captured those. If I say, does copper 2 sulfate dissolve, you are able to know, even without doing it practically. Yeah. Now let us look at preparation of salts. How do we prepare them? Oh, look at those tins. Those tins are full of salts. Does it mean we just get them from the ground? No. See, we prepare them, and these are prepared on the large laboratory scale in the industries. See. Now, laboratory preparation of salts. And this one I think we shall demonstrate very fast, and we try to see the properties. Now, we are starting with A, soluble salts. Soluble salts. How do we prepare soluble salts? Now look here. We say the salt, you just react an acid and a base. But also, if we remember very well, we looked at the reaction of an acid with a metal that produced salt and hydrogen. Huh? Now, look here. The methods include, the first one is reacting a metal with an acid. Didn't we say that is possible? Because we said metal plus acid, you get what?
Hydrogen.
And hydrogen. Yeah, that means soluble salts can be prepared by that. Which example would be here? Like which soluble salt can you pick out and which metal could you use there?
You can use a metal like sodium.
Sodium metal. And which acid?
Hydrochloric acid.
Now listen. Iron filling sand, sulfuric acid. Which salt would be that? Would be now iron? So, now listen very attentively here. Shirava has told us that we can use sodium metal. There are some metals, as we shall look in the next two topics, what we call reactivity series. There are some metals on earth here which are very, very reactive. That is potassium and so. When you try to add an acid, the reaction is violent and explosive. See, if only water can make a metal be violent, what of if the acid is used? That means some metals which are very reactive, we don't use this method. Like sodium, we don't. We can use magnesium. Magnesium sulfate would be prepared from what? Magnesium, not so? Plus sulfuric acid, we get magnesium sulfate plus what? There you are. You see? Now look at the next part. Is reacting an acid with metal hydroxide. A metal hydroxide is in under which group of substances? There you are. It's a base, not so? Or metal oxide, which is also a base. See? Oh, that means acid plus base gives us salt plus water. Now, could somebody help me? Which salt could you prepare from this combination? You mentioned which one base, one acid, one product. Because now we are going to pick one here and describe one here, and our we shall have finished with that.
Sodium hydroxide
Sodium hydroxide plus
hydrochloric acid.
Then we get
Sodium chloride.
hydrochloric acid. We get sodium chloride plus water. That's very great. Now, there is the last one here which we shall not go into very much, reacting an acid with a metal carbonate. An acid with a metal carbonate. This one might be new to your head, that acid plus a metal carbonate, what do we get? Of course, we must get the first product as what? As what? What we are looking for is a salt, not so? Plus now, because of that carbonate part, there is of course our water, then plus a gas called carbon dioxide. This gives 3 products here for a carbonate because of the carbonate. Oh, give us one example here. Sorry.
Sulfuric acid.
With sulfuric acid plus zinc. Actually, our carbonate. Therefore, we get zinc plus carbon dioxide. Now, within the interest of time, I'll pick one here, one method, because all will have the similar things here. I'll pick that magnesium, preparation of magnesium sulfate crystals from magnesium a metal. I want to prepare one here. I have the magnesium ribbon is there, and my sulfuric acid. I hope I still have it here. It's there. Now, this preparation I will demonstrate. Then we shall discuss as I demonstrate. Keep time. Keep time, because should we now example? Because we want to finish soluble, then got one insoluble, we switch on. We others, I'm going to ask you to search for this. In fact, I will give assignment questions on each here. Yeah. Now, that is our subheading, preparation of magnesium sulfate from preparation of magnesium sulfate crystals from a magnesium metal and dilute sulfuric acid. We don't normally use concentrated here, we use dilute ones because they are the ones that can produce for us that basic unit of an acid called hydrogen When the acid is concentrated without water, it is unable to yield that active part, therefore might fail to produce hydrogen. See? Yeah. It will produce certain things which are not what we want. Now, preparation, let us discuss over this. Now I'm going to show you, then we discuss the steps. That means preparation of dry crystals of magnesium what? Sulfate. Using what? Magnesium metal, not so? And which acid? Dilute sulfuric acid. Now me, I would ask a question before I discuss this. Could magnesium oxide work? Can it work? If you use the magnesium oxide and what? And the acid, would it work? It can't work.
Because there is a base and this one is a salt.
No, if it's a dilute sulfuric acid.
With magnesium oxide, can it work?
Yes.
Nice.
Because this one is a base and this one is an acid.
Because there is a salt and this one is an acid.
No, the salt is magnesium oxide. Really?
Girls, you are speaking new chemistry which I don't understand.
It is the hydrogen ions or oxide ions. Not just asking about
A base is made of?
hydrogen ions or oxide ions.
Correct or incorrect? Basic unit of a base is? What makes up a base? Which ions? Hydroxide ions and or oxide.
Yes. And then you ask for magnesium oxide.
I mentioned wrongly. The question is preparation of magnesium sulfate from magnesium oxide. Can it work with dilute sulfuric acid? Can we prepare magnesium sulfate from magnesium oxide and dilute sulfuric acid?
Next, you said.
Chirabo Kiraimus, yes.
Because if we are to say from magnesium oxide,
Yes.
magnesium oxide is a base. And then the dilute
Acid.
sulfuric acid is an acid.
Oh.
But how about magnesium sulfate? Because they said preparation of dry crystals.
Of this from that if we are adding magnesium oxide plus dilute sulfuric acid, do we really get the product? Do we get magnesium sulfate?
Yes.
Do you mean Chirabo seems to be correct or incorrect? That means possible. Right. Is it possible also using magnesium carbonate?
Yeah.
It is possible. That's very good. See. Thank you. Now that is a bit. Now look here. How do we do that? How do we do that? How do we do that? Now what we do, we get a glass beaker. Because of time, we shall not wait for all the steps to be over. This one will be in one of our project works. Now what we do, we measure a reasonable volume of the acid. Like we can fill a beaker halfway with the acid. with sulfuric acid halfway. That's around 250 cubic centimeters. Then we add in pieces of magnesium ribbon, tiny pieces. We can add magnesium powder. It's better to use the metal in powder form or in small pieces, but when we use granules it will take a long time to dissolve. The best thing, we can use a powder of the metal. You get that? We can use a powder, but since we don't have a powder, this is a demonstration. You can scoop a powder of the metal. You add and you stir. When you stir until it dissolves. But if we have a ribbon, we can't know the amount very well. It's better use a powder. You add magnesium powder, you stir, and it dissolves. You see that? Then you keep adding as you stir until no more can dissolve. That means when you have reached a saturated solution, you add, you stir, stir until no more dissolves. We get that right?
Yeah.
Now when no more dissolves, then we can transfer that mixture to a filter paper and we filter. Listen. We said add 1 spatula at a time. Are we saying this? Add 1 spatula at a time. 1 spatula at a time. 1 spatula at a time as you what? You stir. When no more can dissolve here, no more can dissolve, meaning you will see the solid at the bottom. Is that correct? But when you add magnesium to an acid, you will see a gas coming out. Let me use the ribbon, though we are not very much. When we add the ribbons, I think you're seeing how they are reacting and bubbling. Yeah. There is a lot of bubbling. That bubbling is given a chemical word called effervescence. That means we shall introduce in another term there, that when you see bubbling, you call it effervescence. Now, you see that the piece has disappeared. If you have enough, you can add more until the pieces can no longer dissolve. But if we had powders or granules, we would keep adding them. Is it? Now there is effervescence of a colorless gas called hydrogen. You keep stirring. Now when you stir, it will dissolve. It has dissolved. But you keep adding until it refuses to. That means you reach the saturated solution. After that, you filter off the undissolved part. You would filter off the undissolved part. In case it didn't dissolve, filter off. Then you would get a colorless solution of magnesium sulfate down here. After getting that colorless filtrate, on the filter paper will remain undissolved magnesium metal granules. Now what we do, we transfer this the colorless filtrate to an evaporating dish. Let me just use it as a demonstration. We transfer it here. Then our wire goes here. We transfer it here. Then we we heat. You heat until the water is halfway, until the solution is halfway the original amount. That means you are trying to evaporate all the water to make the solution reach what we call a saturation point, a point where you have almost only the salt left in the solution. Now when you heat to saturation point, you remove and put it down to cool, or you put in a water bath. You take in a basin having water, you leave it there to cool. When it cools, because of time, this will take some time, we can do it in the project work. When we cool, you will see, because magnesium sulfate is white, you will see white suspensions starting to what? To form. You will see as if this. When you cool a colorless hot solution which is saturated, you are going to see this. You will see a suspension like this. Then when you see that, it means you have formed the magnesium sulfate crystals inside. You now refilter to remove the liquid part, and you remain with the crystals. After refiltering, you wash it with a small amount of water. Now that is another stage of filtering a hot mixture. Let me show you that, what I'm trying to mean here. I'm filtering these white solids here. When you filter off, it didn't go the whole of it. There's some little water. Okay. When you filter like that, the white crystals of the manufacture of the prepared salt will remain on the filter what? On the filter paper here. Then you try to wash. Now listen, how do you wash a solid on the filter paper now? There you are. Now, during washing you open a filter paper, because of time, to save time. You see our white particles are still here. What we do, we get water using, we get distilled water, but it's better you if the salt is very small, use a dropper. Pass a few drops over the salt slowly. When you pass a lot, it will just wash away the salt. Then after washing with the little drops of water, then you get another filter paper. What is the use of it? To dry this one that is there. Then you remove. Can get another one if it's not totally dry. You see that when you remove, you will see some fine white particles of magnesium sulfate there. Yeah, that's what we mean. That what we do here, what do we do? Fill a beaker with dilute sulfuric acid. Now, how do we prepare this? We said fill a beaker with dilute sulfuric acid, then add magnesium powder or magnesium tannings. Now listen, we said that small pieces of metals are given names, filings, tannings, granules. That now when we say add spatulas of magnesium tannings, one at a time while stirring. Clear? Until no more of the magnesium tannings dissolve. Is that right? Until no more of the magnesium tannings dissolve. Filter off until no more dissolves. Then you talk to us that there was vigorous effervescence of a colorless gas called hydrogen gas. Clear? Then you tell us next that filter off the undissolved granules to obtain a colorless filtrate of magnesium sulfate. Clear? Then transfer the colorless filtrate to an evaporating dish. Heat the filtrate strongly for some time until almost the whole water has evaporated by obtaining half the original volume of the mixture of the solution that you put. Remove the evaporating dish from the heating source. Leave it to cool. Crystals will begin to form in the solution. The crystals of magnesium sulfate are now filtered off, washed with a little distilled water, and dried between pieces of filter papers. That's the same that you do to here. If you are reacting an acid with a metal hydroxide, like if you wanted to make magnesium sulfate from magnesium oxide, you would say fill a beaker with dilute sulfuric acid, but of course oxides are normally less reactive. They need some heat. If you are using an oxide, you must heat. You must say fill a beaker with warm dilute sulfuric acid, add magnesium oxide powder a little at a time while stirring until no more dissolves. Filter off the undissolved magnesium oxide. Transfer the colorless filtrate to an evaporating dish. Heat strongly until most of the water has evaporated so that the solution remains halfway. Put down to cool and filter again. Wash with distilled water, dry between pieces of filter paper. Anybody with a problem there? Does it seem any hard? No. Even a carbonate you do the same. Let us go to, yes, Chirabo?
If you want to make copper sulfate,
yes,
and you're using the copper hydroxide, will it give you the very same color of copper sulfate blue?
Yes. You already know that copper sulfate is blue? Okay. Yeah. Now let us turn it to insoluble salts because of minimizing time. Insoluble salts. Salts that don't dissolve. Can you give me one example? Yes? Okay, now wait a little bit here. The next discussion is on insoluble salts. Clear? Now listen. Before insoluble salts, under soluble salts, we have seen how many methods. We reacted acid with the metal. Not so? And we said do not use a very reactive metal because the reaction is violent and explosive. Then we have seen acid plus base, then finally acid plus carbonate. But there is what we also call direct synthesis under the direct what? Synthesis. To prepare, listen, direct synthesis. The word direct means there are no many steps of mixing, filtering, and so on. Clear? Now it is used to prepare majorly what we call the salts which have a behavior of when you leave them exposed. Listen, when you leave them exposed, you'll get the tin when they have changed into a solution. You even wonder where water came from. There are some salts which normally absorb water from the surrounding atmosphere. That's why we don't advise, like that sodium hydroxide, if we opened it now, that tin, tomorrow you'll find it wet. After a week you'll find it in solution form, meaning it is absorbing water from the atmosphere. There are some salts which are like that, and those salts too, which absorb water, are called deliquescent. Yeah, the tendency to absorb water, deliquescent salts, are those salts which normally absorb atmospheric water vapor and dissolve in it to form a solution. Now those salts are prepared by what we call direct synthesis. There are so many here. Direct synthesis, we mean it's a one-step reaction giving you the product. No need for indirect routes of passing here, dissolve, mix, filter, no. It's direct. Which salts are those? There are salts like, say, iron 2 sulfide. In fact, we can just iron sulfide. Iron sulfide. Iron 3. Don't add that word 2 in bracket. We shall see its meaning later. Iron 2 sulfide. What do we mean by 2? That 2 is a certain identity. It has a very big meaning, but we are going to see it ahead there. Iron 2 sulfide, iron 3 chloride. Yeah, those are prepared by direct synthesis. So you just get the elements, mix them, get the product by heating. Like here you get iron plus sulfur gives iron 2 sulfide. You just heat a mixture together. Okay. Now let us go to insoluble salts. See, insoluble, those that don't dissolve, and I will pick one example here. I'll pick calcium sulfate. Is it so insoluble? Which ones are you giving me?
Zinc carbonate.
Zinc carbonate, yes. What else?
Lead to sulfate.
Lead to sulfate. Lead to carbonate, yeah. But me, I'm going to talk about preparation of calcium sulfate only, yeah. Let us rush through very fast. Preparation of calcium sulfate. Before that, now, look here. See, look here very, very attentively. There is what we call double decomposition, or what we call precipitation. Look here, AB plus CD can change into products by exchanging parts. A can go with D, whereas B can go with C. This is called a double decomposition process, a process in which parts are exchanged to form products. Now listen. Insoluble salts are not prepared from the methods we saw up there. Clear? Because you see, when they are insoluble, they will interfere with the substance that you've added. Because you form them, they don't form a colorless mixture. Therefore, they will keep interfering. If you are adding calcium metal to sulfuric acid, you are forming again something that is not dissolving, yet you are adding something, a solid. It means you will interfere with the reaction. Now, they are prepared by a method called precipitation, or we call it double decomposition. Yeah. Double decomposition. Now listen. What is that? Let me get for you something here. E.g., AB plus CD gives us AD plus BC. Not so? Now, I'm pausing there and put this one here. And let me put this. Calcium chloride. Is it a soluble salt? Let me have asked a question. Is calcium chloride soluble? Plus sodium sulfate. Is it soluble? Soluble. Now, look here. From this consideration, I'll form calcium, calcium sulfate plus sodium. Now, listen very, very attentively. Is calcium sulfate soluble? No. Is sodium chloride soluble? I'm sure all salts, it is soluble. Now, when you mix two soluble salts to form insoluble, we call that one double decomposition, or we call it precipitation. So, precipitation. Now, listen here. What do we mean? Now, look here. Let me ask a question. This is colorless mixed with colorless. Clear? Let me demonstrate it here so that somebody can know what we are talking about. Colorless is here. I'm mixing with another colorless. Do you see this? Now listen. Colorless plus colorless has formed white. Well, now this one is no longer called a suspension because you didn't start with water. This is now called a precipitate. There you are. We are in deeper things here now. Emulsion. See. Now emulsions are now in your now in what? That language is used majorly in biology. Emulsion. See. Now listen. Let us come to our senses first. Do you see that there is a white solid, white insoluble substance formed here? I mixed colorless plus colorless, got this with a clear solution up, showing that there you are. There is a watery part here. It's sodium chloride. See. Now listen now. When a soluble salt and a soluble salt are mixed and you form an insoluble salt, the mixture is not called a suspension. A suspension is formed when an insoluble compound is put in water and it doesn't dissolve. But when you are forming an insoluble salt yourself, the product you are forming is called a precipitate. Therefore, this is called a precipitation reaction. That insoluble salts are prepared by precipitation, which is a reaction between two soluble salts to form an insoluble salt and a soluble salt. It is a reaction between two soluble salts to form an insoluble salt and another soluble salt. Now, listen. Now, we want to discuss how you prepare calcium sulfate, because many insoluble salts, you can just pick two soluble salts. Just look at the parts of the insoluble salts, choose good soluble salts, let them give you that product. Like if you wanted to prepare lead 2 sulfate, which salts would you mix? You'd pick one soluble and mix it then. Lead 2 sulfate must have who? Sulfuric acid. She's again, you see, that even instead of using what? Using anol, you can use a soluble salt and an acid, because it will do, these are both colorless, therefore it will form calcium sulfate. Now it will create another acid from this. Because of this acid section, it will be hydrochloric, because chlorides come from hydrochloric what? That means calcium, there you are, calcium chloride plus sulfuric what? Acid must give us calcium, because salts from sulfuric acid are called what? Sulfate. But because there is a chloride, it will form the chloride and the acid part. Expressions were the question? Hydrochloric acid. Yes? Sulfide and the sulfate. Now you see that the chemical name is sulfate.
No, like the name of the acid that forms the sulfate.
Now the sulfide is formed from now that is deeper. Listen now. Sulfates are formed from sulfuric acid, not so? See, but sulfides, there is no sulfide acid. See, but they can be prepared from direct synthesis, like you saw. Sulfur salts, iron plus sulfur, you get iron 2 sulfide. See that? Direct synthesis salts by mixing. It means sulfides are salts from sulfur. Sulfur is a non-metal. When you heat it with a metal, sulfur is yellow. Heat it with iron, it will give you a black substance called iron sulfide or iron 2 sulfide. That means sulfides are not derived from acids, but by direct synthesis of a metal and sulfur. See? Now, look here. How do we prepare calcium sulfate? You were saying lead 2 sulfate is prepared from sulfuric acid and but lead 2 sulfate is insoluble, because it must be a soluble salt and an acid, or a soluble salt and another soluble salt. we are seeing that most of the salts of lead are insoluble except lead 2 nitrate. You'd mix lead 2 nitrate plus sulfuric acid. What would you get? Lead 2 nitrate plus sulfuric acid you'd get. And there you are. Lead 2 nitrate is the only, you can't use the lead 2 chloride because it is insoluble, plus sulfuric acid. What do you get? You said lead 2 sulfate and who? And nitric acid. Very good. Because there is this acid in that. So you see, these salts are so good. See that? Now listen, how do we prepare this? Let me just explain and demonstrate this. Look here, because of time. We get, listen, we get, look here, we get a known volume of calcium chloride solution, a known volume of calcium chloride solution, see, clear. Then add another known volume of sodium sulfate solution. You can add an equal volume mixed with equal volume. When you pour them together, let me use this as a demo. Now when you pour them together, you'll see this. This one is called a white precipitate because it's formed from 2 soluble salts. Then you filter. Then you filter. What you have formed here, that white thing, is what we are calling the calcium sulfate. You would filter. You do filter off this white precipitate. When you filter, you'll get on the filter paper a white substance. That white substance, you wash it. Do you remember how to wash? Yes. Passing a little water. Then you dry that. You'll have got calcium sulfate. Clear? That a known volume of calcium chloride is placed in a beaker. An equal volume of sodium sulfate is added. The mixture is stirred well and filtered. The white precipitate is filtered off, which is washed with distilled water and then dried between pieces of filter paper. Okay, now let us go to properties of salts. Properties of salts, and in trying to close properties of salts. Person, are you at par? Yeah. You are at par. Properties of salts. We look at solubility in water. Then you look at color of salts. Then precipitation of salts. And we shall, the color, we have already seen colors of salts. All nitrates, I mean, we have seen solubility. All nitrates are soluble. All carbonates are insoluble. Let us look at the color of the salt in closure. That is basically what we have only we are left with. Precipitation, we have seen that when you mix two soluble salts, you form a precipitate. Colors of salts. Are we on that heading there? Now, I want you to look at zinc carbonate inside there, and you look at zinc sulfate, and you tell me the color. Zinc carbonate and zinc sulfate. What is the color? Patience. Zinc sulfate and zinc carbonate.
Whitish, brownish. Zinc sulfate.
Zinc sulfate. Look at it very well. The all color. Is it contaminated inside there? Oh. Okay. Look at zinc carbonate and zinc. What do you have there?
Zinc sulfate. This is copper sulfate.
Copper sulfate. Leave this one, and we look at zinc carbonate and look at copper sulfate. What is the color of zinc carbonate?
It's white.
White, not so? What is the color of copper sulfate?
It's blue.
Blue. Now, if we looked at another copper salt, maybe copper chloride or copper nitrate, we would find out that it's also blue. Zinc carbonate is white, zinc sulfate is white, zinc nitrate is white. What do you look at? What could run to your head if I asked you to remember? Zinc carbonate is white. Zinc sulfate is white. Zinc chloride is white. What would run into your head to remember the color of salts? Like copper sulfate is blue. Copper 2 sulfate is blue. And copper 2 nitrate is blue.
Copper carbonate is blue.
Blue. But copper carbonate has just a divergent color a little. It is green. What would run to your head that would make you to remember the color of a salt? Yes, Chirabo.
Okay, when it comes to the zinc metals and it's connected to zinc, that's white.
The color is decided from the metal ion that is present. Yeah. That very clear? That means we take that note down very fast, that what determines the color of the salt is the metal ion that is present in the what? In the what? In the salt. And we shall summarize here: metal ion, then the color. Now, salts of these are all white. Salts of potassium, salts of potassium, sodium, calcium, magnesium. That means you can recall the colors in case you are asked. You don't need to be taken to the laboratory to know the colors. You know one, you know all. See? Barium, silver. When I say what's the color of barium sulfate, you know. Lead, you see that? Ammonium, anything ready with those is white. See? See that? Calcium, ammonium, aluminium are all white. Zinc are all white. That means the salts are white solids, but when you dissolve a white solid in water, what do you see? Like salt at home, if you put in water, what do you see? If you put salt in water, have you ever cooked? If you put salt in water, it turns. Like you added zinc sulfate to water, what did you see?
Zinc sulfate to water, it remained colorless.
The salt dissolved to be colorless, not so? White solid, that means they form colorless what? Solutions. Now, somebody is doubting zinc carbonate. It's because it didn't dissolve. All soluble salts must give colorless solutions in case they are white. But if it's an insoluble salt, it won't dissolve, of course. You know, that will form a suspension. A solution is only formed when the salt is soluble. That's very, very correct. Now, copper salts, for them they are blue except just very few, like copper 2 carbonate, copper 2 carbonate. That means you can know. Yeah. Iron 2 salts are green, e.g. iron 2 sulfate. Then iron 3 salts, iron 3 are yellow or brown. I think you're saying there is some key symbol here, 2 and 3. We are going to look at it in the periodic table in the next topic. That what do we mean by that 2 and 3? Yeah. Now those are some of the properties of salts, and if you ask the color, you know. Now lastly, uses of salts. Uses of salts, and that one I will ask you to go to Google. You mention a salt, magnesium sulfate, used for what? But for the meantime, the so common salts that we know their uses is the one we use at home is, what was the name that we said? Sodium chloride, which is used in flavoring food. See, it means uses of salts we are able to know. You mention a salt, sodium chloride, used in flavoring food. Sodium carbonate, which is called the soda ash, used to soften hard water and also making glass. Did you remember materials? Sodium carbonate was used in glass. Clear? Now, let us put a few uses for about 3 salts, then I'm going to ask you to look for more examples. Uses of salts. We say the sodium carbonate is also called the soda ash. That clear? You use it to soften hard water and also in the manufacture of glass. If you remember our materials in senior 1 work, are you there, Patience? Yeah, that's right. Sodium chloride is flavoring foods, not so at home.
Yes.
Clear? Yeah. Which is normally called the normal salt. Yes, Patience, you have a very strong answer. It's burning.
Sodium hydrogen carbonate, baking soda is used during baking.
Exactly, sodium hydrogen carbonate. Baking soda. See, yeah. Now class, you'll get more for yourselves. Clear? Now that's the end of salts. That fine? Have this activity of integration. then we echo through what we have said today. Activity of integration. Yeah. We read it for you. Yeah. You know, salts are all around us. You eat them in medicine. Same. Activity of integration. Your friend is involved in planting oranges. Your friend is involved in planting oranges. However, his crop is showing yellowing of leaves. However, his crop is showing yellowing of leaves. When he contacted the area agriculture officer, when he contacted the area agriculture officer, he was told that the soil lacks the element nitrogen. The soil lacks the element nitrogen present in the form of salts. The element nitrogen present in the form of salts. Continue. As a chemistry student who has learnt about salts, as a chemistry student who has learnt about salts, and how salts are prepared, and how salts are prepared, design a procedure that you can use to prepare salt. Design a procedure that you can use to prepare salt. Containing a salt containing the essential element, containing the essential element for your friend to be used as a fertilizer. For your friend to be used as a fertilizer. So, yeah, thank you very much. We meet again in another discussion of the next topic. Yeah.